Hi, everybody. I thought I would go through some of the answers to the quiz that we had. And these were all the same questions as problem set 2. So the answers to problem set 3 are basically the same as the answers to these. So we start with our regression equation. COVID deaths as a function of mask mandates. The independent variable is mm. The coefficient is negative 0.15. And that means for each 1 unit increase in mask mandates, COVID deaths go down. COVID deaths per 10,000 goes down by 0.15. So if COVID deaths before on average were 7 deaths per 10,000 people. When the mask mandate increases by 1, instead of on average being 7 deaths, go down by 0.15, so it will be 6.85 deaths. There were people who somehow got a calculation of 1,500 fewer deaths, but that's not don't recall exactly how they'd interpreted it. But the number of COVID deaths usually be on the order of 8 per 10,000 or 10 per 10,000. So a 0.15 decrease is substantial in terms of death rates, but it's a small number. To get to 1,500 fewer deaths, you'd be talking about population of 10 million people to have the mask mandate increasing have that big of an effect. So remember that COVID deaths is deaths per 10,000. It doesn't mean you multiply the coefficient by 10,000 to get the number of deaths. Be careful, as we'll see in class, throughout, interpreting coefficients is important. So 0.15 fewer units of the outcome variable, which is deaths per 10,000 people. Many of you calculated correctly. If Rita has an MM of 40, mass mandates of 40, then 40 times negative 0.15 is 6. 80 minus 6 is 74. If her actual number of deaths is 100, then 100 minus 74 is 26. So the residual is 26. 100 is her actual number of deaths, and 74 is the county's predicted number of deaths. So the predicted number of deaths COVID death hat predicted would be 74. So actual minus predicted, Y minus YI hat, that would be 24. Test the null hypothesis. Well, for that, you needed to calculate the t-stat. The t-stat is equal to beta's 1 hat minus beta 1 null, which is always 0 in our case, divided by the standard error. So we have negative 0.15 over 0.05, which would be equal to 3. So the t-stat is equal to 3, and then our formula for calculating the probability of observing a t-stat as far away from 0 as 3 is 2 times p-norm of the absolute value of 3, the negative of the absolute value of 3. So that'd be a pretty small number, and we would reject the null hypothesis that the coefficient's equal to 0. We would reject that null hypothesis because the p-value would be less than 0.05. Confidence interval, I don't know, that there were a few people got it wrong. Look at the chapter 4. R-squared tells us how much of the variation in the outcome variable, that is COVID deaths, is explained by variation in mask mandates. So it's a simple definition. It's the same thing every time. There's not a different definition. It's how much of the variation in the outcome variable is explained by variation in the X variable in mask mandates. Suppose you knew the total sum of squares. I don't know that anybody got that wrong. If you got it wrong, it's because you used the wrong formula. R squared is equal to 1 minus sum of squared residuals over total sum of squared over TSS. Sorry, I'm using the disappearing one. Some people wrote 1 minus SSR, the whole thing divided by TSS, which is obviously wrong. So make sure you know that formula. Suppose the explanatory variable, now we interpret the coefficient as the difference between the 1 category and the 0 category. So counties that got these grants had 0.25 fewer deaths per 10,000 people than counties that did not get the education and promotion grants. That's how we interpret the coefficient. Here, the t-stat is negative 0.25 over 0.15, so that's less than 2. So we can use our rule of thumb to say that we probably will not reject the null hypothesis. The p-value will be larger than 0.05 because we know that our rule of thumb is 1.96 or 2 rounded is roughly the cutoff point for our conventional decision of whether to reject or accept the null hypothesis. Let's see, we did that. The assumption here is that the expected error conditional on the levels of x is equal to 0, the expected value of the errors, and that condition is met when whatever we mentioned in class, there are no likely confounders. That is, there's no omitted factors that are correlated with the x variable, in this case with mask mandates, and determining the outcome variable. Now, if the mask mandate grant has been randomly allocated, as in the second case, then by definition, it's randomly allocated. It's not correlated with anything. So the error term, that is all the other factors in the measurement error, are not correlated with whether you got the grant or not, because it was determined randomly. So the assumption is likely met, and we have no problem. With the first regression, however, the level of mask mandates is probably correlated with other factors, whether people like to congregate, whether people are smokers, whether people respect county health officials. So all of those other factors are likely correlated with the level of the mask mandates. So the assumption is likely not true, and our regression is likely not valid. And write down the OLS coefficient. I think everybody got that. If you didn't, you need to review your notes. So great. People in general did good on this quiz, and that was a little review.